Hello students, once again welcome you to GK's Maths classes. Today, in continuation of applications of differentiation, we are going to do the next section of application of differentiation, that is maxima and minima. And you all know this is a very important section of your syllabus involving applications of differentiation, because definitely you will get a 5-mark question or a case study questions from maxima minima, and also there is a possibility that you will get some MCQs or even a 2-mark question from maxima minima. So I can say the weightage is around 6 marks you will get in the board exam. Okay, so it's a very important chapter, and it is a slightly lengthy chapter where the problems are a little lengthy also. So I hope you will understand what we are doing, and in case you have a doubt, you can always put your doubt in your comment section where I will get back to you. So let's straight away get inside this chapter. Okay. Now what is this? What is it called? Maxima and minima. Okay. Now for example, I have a function, say y equal to f of x. Okay. Let's take a function y equal to f of x is a real valued function. When I say real valued function, that means my range is a real number. Y equal to f of x is a real valued function, and it has two variables, say x and y. And you know, graphically every function represents a curve. Okay. Suppose I represent this function by a curve like this. Okay. I represent a function by a curve like this. Of course, it can extend, but I'm just for our comfort, I just leave it here. Okay. Now let me mark this point as A. Okay, somewhere here, and take this point as B. Okay, and I will say this is C. Okay, see, this is a curve from A to C. Now what I do is, first I will break the curve into two parts. The first part of the curve is, I will say, along AB. When I go from A to B, what type of function it is? You know, this part of the curve is an increasing function. Along AB, the function is increasing. If the function is increasing, you know definitely your dy by dx is going to be positive, because you know, for an increasing function, the derivative is always positive, because the tangent makes an acute angle with the positive direction of x-axis. Okay, so from A to B, it's always increasing, so dy by dx is positive. Now I will say along BC. Now if I look at it from B to C, you can see the function is decreasing. If the function is decreasing, obviously derivative is negative, because the tangent is going to make what angle? It will make an obtuse angle with the positive direction of x-axis. Okay. So now when I go from A to C, my dy by dx is changing from positive to negative. So when you move from positive number to negative number, you definitely have to pass through 0. Correct? So that is the point where the tangent is going to be parallel to x-axis. You see, this is the point where the tangent is parallel to x-axis. So I will say at B, my dy by dx is 0. When I say dy by dx is 0, that means it's the point where the tangent is parallel to x-axis. Okay. Now, what is this point B? What is the significance? We'll come to that little later. Okay. Now, when x increases, that means when x increases, that is when I move from A to C. When I say x increases, that means I am moving along the curve from A to C. What happens to my dy by dx? My dy by dx change from positive to negative. If my dy by dx change from positive to negative, then I can say the function has local maxima, as local maxima at the point B. The function has local maxima at the point B. Okay, now we'll go into the details little later. Now this process is called first derivative test. First derivative test. This is called first derivative test. Now what I want you also to understand is, so when x increases, dy by dx changes from positive to negative. That means the value of dy by dx, now you look at dy by dx as a new function. When you look at dy by dx as a function, when x is increasing, this function is decreasing because it is taking values from positive to negative. That means dy by dx is a decreasing function. So if dy by dx is a decreasing function, I can say the second derivative, the slope of dy by dx. What is slope of dy by dx? D square y by dx square. And dy by dx is decreasing. Why? When x increases, dy by dx changes from positive to negative. When it is from positive to negative, the values are decreasing. So dy by dx acts as a decreasing function. So when dy by dx is a decreasing function, its slope, what is the slope of dy by dx? Slope of dy by dx will be d square y by dx square. And for a decreasing function, the derivative will be negative. So this is called second derivative test. This is called the second derivative test. Okay, so y equal to f of x is a function. Every function represents a curve. If the curve is like this I say it's like a mountain, okay, or it's like a mountain, okay, then I can say the function has a local maxima at this value, at the point B. And for the first derivative test, this till here is the first derivative test. That is when x increases, when I move along the curve, if my slope changes from positive to negative, then you can say the function has local maxima. And for second derivative test, since dy by dx is a decreasing function, its derivative will be negative. Okay, so first let's understand the process, then we'll go once again and understand what local maxima, local minima and all that. So this is one particular situation. Now what is the second situation? Suppose I have a function, say y equal to f of x. Okay, and understand it represents a graph. I draw the graph like this. Okay, I start from A and I reach C, passing through B. The same process along AB. Along AB, what do you suggest? Along AB, you can see the function is decreasing. When x increases, y decreases. It's a decreasing function. Since it is a decreasing function, its derivative will be negative. Its derivative will be negative. Again, along BC, you see the function is increasing. So what do you say about its derivative? Its derivative will be positive. Its derivative will be positive. Okay, so when you are moving from negative to positive, definitely you have to hit 0. So where will that 0 be? At B, dy by dx is 0. This is the point where the tangent is parallel to x-axis. The tangent takes a turn, okay? It takes a turn from negative slope to positive slope, passing through 0. Then you can say when x increases, here also x increases, that is along this. When x increases, or when you move from A to C, your dy by dx change from what? Change from negative to positive. If dy by dx change from negative to positive, you can say the function has local minima, local minima at B. And this is called first derivative test. I'll call it first derivative test. Now, you can see clearly when x increases, dy by dx is increasing. From negative, it is going to positive. It is going from negative to positive. It is keep on increasing. So when it is keep on increasing, you can say dy by dx acts like an increasing function. So its derivative, what is the derivative of dy by dx? D square y by dx square will be positive. For what? For local minima. This is called second derivative test. It is exactly the reverse of maxima. This is for local maxima. This is for local minima. See, this is like a valley. The curve looks like a valley. So if the function represents a graph like a valley, it has a local minima. Okay. Now we'll go to another situation. What is the next situation? I have a function, say y equal to f of x. First we'll come up with all situations, then we'll put everything together. I have a function, say y equal to f of x. Now suppose it represents a graph like this. And I will show you later, maybe in the next class, all these things using GeoGebra also. So this is the curve. Okay. As usual, I'll mark this as A and I call this as B and this is C. Now look at it. Along AB, what type of function it is? Along AB, the function is increasing. It is always increasing. Can you see? It's always increasing. So dy by dx is positive. The slope is positive. Now along BC, what do you say about the function? Once again, it is increasing only. So here also, dy by dx is positive. Okay. So when I move from A to B, you see the tangent is always positive, but at B, the tangent will be parallel to x-axis. So I will get it as 0. Tangent is parallel to x-axis. So that is 0. Okay. Now, when x increases, that is along this, okay, when x increases, dy by dx, no change in sign. There is no change at all. Dy by dx do not change its sign. It always takes positive values. It comes to 0 and again it continues to take positive values. Then you can say the function has point of inflection. Function as point of inflection at B. This is once again called first derivative test. Okay. Now look at the second derivative. It's very simple. How do I understand no change? No change means there is no change. So how do I understand no change in dy by dx? So d square y by dx square, okay, will be 0. Suppose I say the velocity is uniform, then the acceleration is 0 because there is no change in velocity. So no change in velocity means derivative of velocity will be 0. Similarly, no change in dy by dx. So its derivative will be 0. Interesting, isn't it? So once d square y by dx square is 0, you can conclude, you can say second derivative test, second derivative test fails. So if you get second derivative as 0, you can say second derivative test failed. Okay. Then what I do? Do first derivative test. I am writing it as FDT. Do first derivative test for what? To confirm maxima or what? Minima or point of inflection. I'm writing POI, that is point of inflection. Now, one thing you should remember, if the second derivative is positive, the function has local minima. If the second derivative is negative, the function has local maxima. But if the second derivative is 0, you cannot conclude that it is point of inflection. All that you can conclude is the second derivative test fails. Now, when second derivative is 0, there is a possibility that it can be point of inflection, it can be maxima or minima. That can be confirmed only using first derivative test. We do second derivative test because it is much more easy and it's not tedious to do. That is why we follow second. Otherwise, you can say first derivative test is more a confirmatory test for maxima and minima. Okay. Now, this is one situation. You can have another situation like this. This must be easy to understand. Y equal to f of x is a function. Let us assume it represents a graph like this. Okay. And whatever I want, I'll take from here. One second. All this I want, so need not write again and waste our time. So I'm having it here. Let it be there. Okay, now this is my point A, and this is point B, and this is point C. Along AB, the function is decreasing, so it will not be positive, but it will be negative. That's a change. Now, along BC also dy by dx is negative. Now, when x increases, dy by dx, no change in sign. Therefore, it has point of inflection. So it can be like this, or it can be like this. The slope need not change from negative to positive or positive to negative. It can be positive to positive, negative to negative. It has point of inflection. Okay. Here also you can say second derivative test will fail. Okay. Now, so these are some of the things that you should know about maxima and minima, especially about local maxima and local minima. Now, just see this. Suppose I have a graph like this. Okay, just some random graph. Okay, it is extending. I am not giving it in an interval. It is all over. Okay, now this point A, and I call this point as B. This point A is called local maxima. Okay, and the point B is called local minima. And these points A and B are also called critical point. Otherwise, you can call it turning point. That is where the curve takes a turn from positive to negative or from negative to positive. So these points are called the critical point, otherwise called the turning points. Okay. So if I say this is a function has two maxima and one minima, then immediately you can visualize the curve. It has two maxima, so the curve has to be like this. It has two maxima and one minima. So this maxima minima concept is also used to visualize a curve. Okay, exactly you can draw the curve, but to give you a gist of what the curve will be, this concept will definitely help you. Okay, so now we'll go back to this particular page. Look at this. Here I have talked about local maxima and local minima. This is all given in the NCERT book, so I thought I should tell you all this. You can see when I say function is local maxima, okay, suppose this is a maxima. This is the point C. Okay, this is the point C. You see, f of C is this y value. This will be the maximum for every x belongs to real numbers. Okay. So f of C. So in the neighborhood of C, okay, on either side, the values will be lesser than f of C. Similarly, it's the case for minima also, where f of C will be less than f of x. See, if you look at the minima curve, this is your f of C. You can see f of C will be the smallest. F of C will be the smallest compared to all other x values. Okay. Then the critical point term is very, very important. Critical point is a point where the derivative is 0, or you can say the function is not differentiable, both. This is also very important, keep a note. So a critical point is defined as a point where f dash of x is 0, or you can say f dash of x does not exist. Does not exist. Okay. So I hope this is very clear to you. We have understood what maxima and what a minima, local maxima and local minima is. Now I am also going to talk to you about another very important term, and also I want to tell you one interesting thing. Whether it is a maxima or a minima or a point of inflection, one thing is common about all of them. The common thing about all of them is dy by dx will be 0. If it is a maxima, local maxima or local minima or point of inflection, definitely the necessary condition is dy by dx must be 0. Okay? But it is not a sufficient condition, but dy by dx must be 0. Okay. Let's go back to another very important term called absolute maximum, and you can say absolute minimum. Now what is absolute maximum and what is absolute minimum? Already we spoke about local maxima and local minima. Whenever you see local maxima, the curve takes a turn. You have a critical point. Now what is this absolute maximum and absolute minimum? Very, very simple. Now what you do is, I have a function y equal to f of x defined, okay, defined in a closed interval a comma b. Please understand, if you want to talk about absolute maximum and absolute minimum, we need an interval. You cannot have on the entire real line. It should be defined on a closed interval a comma b. It should be closed on both sides. Okay, then only you can talk about absolute maximum and absolute minimum. Otherwise, whichever side is closed, you can talk only about that. Okay, now for this, let us draw the graph. I will just draw one particular graph. Maybe it's like this. This is A and this is B. Okay. So I start like this. Let us assume we have a graph like this. Okay. Now this has how many local maxima? It has 1 and 2. I call it capital M1 and capital M2. Now here I can say capital M1 and capital M2 are local maxima. They are called local maxima. And you can say this is small m1 and this is small m2. The small m1 and small m2 are called local minima. Why? This is where your dy by dx is equal to 0. And these are also called critical point. What is the critical point? Critical point is the point where dy by dx is 0. Okay, so I have got all the points. Now, after that, what I do, I take all these points and substitute in f of x. So I will find, first I will find f of a, then I will find f of small m1, then I find f of capital M1, then I find f of small m2, then I find f of capital M2, then I find f of b. Okay. So now very simple. Just put the values. Suppose this is a, you find f of a. Okay. Now in this you find out which is having the highest y value. Visually you can see f of a has the highest y value. F of a has the highest y value. So you can say this is the absolute maximum. All that you need to do is just find out the y value at the end points and at the critical points. Wherever the y value is maximum, that is called the absolute maximum or maximum value. Okay. The moment that you come across this word local maximum, then it has to be only at the turning point. Whenever you use the word local maximum, that means it is the turning point. But when you say maximum, it can be the turning point, it need not be the turning point. Now, which is the minimum value? F of b. You can see why the lowest value is f of b. So this is called absolute minimum. So this is one situation, okay, where the absolute maximum and absolute minimum occurs at the end points. Okay, I give you another situation. It's the same function. Let me draw the graph like this, where I have suppose this is A, and so this is A, and this is B. So, and this is capital M1, and I call this a small m1. So, what is capital M1? Capital M1 is local maxima. Why? This is where your dy by dx will be 0, correct? And what is small m1? It is your local minima. And they are also called what? Critical points. They are also called critical points, correct? Now, what you do, you find f of a, then you find f of m1, then you find f of m1, then you find f of b. In all this, which is having the lowest value, which is having the, sorry, first we'll talk about the highest value, which is having the highest y value. Definitely it is not f of a, it is f of m1. So in this case, this will be your absolute maximum. So here the absolute maximum do not occur at the end point, but it is occur at a point where dy by dx is 0. So for absolute maximum and absolute minimum, dy by dx need not be 0. See, in this situation, my absolute maximum and absolute minimum took place at a and b, where dy by dx was not 0. Whereas here, dy by dx is 0 at m1. Okay, so absolute maximum means it has to be in a closed interval, and whichever is the highest y value is the absolute maximum. Whichever is the lowest y value is the absolute minimum. Okay, so in an interval, it's when you say maximum, it is absolute maximum. When I say minimum, it's the absolute minimum. Only when we hear the word local maxima and local minima, then the question of dy by dx, because in that case, it cannot happen at the end point. It has to be at the turning point only. So when you say local, the word local maxima means it's a turning point. Dy by dx must be 0. But when it is absolute maximum, absolute minimum, it's in the interval. In that case, dy by dx not necessarily be 0. Now, here you can see this will be a absolute minimum. Here you can see absolute maximum and absolute minimum both occurs where they occur at the They don't occur at the end point like the previous situation. It occurs somewhere in between A and B. Okay, you can have one more situation if you want. You can have, like, for example, I start from here. Okay. This is A and this is B. This is your small m1. This is your capital M1. This is your small m2. So what happens here? Clearly, small m1 and small m2 are local minima, because what is the shape of the curve? The shape of the curve is like a valley, and capital M1 is local maxima. Correct? Now what you do? Find f of A, find f of small m1, find f of capital M1, find f of small m2, and you find f of B. Now in this, visually, which is the highest y value? This is the highest y value, therefore this is absolute maximum. Now which is the lowest y value? Here the lowest y value is at f of m1. So this is absolute minimum. So interestingly here, the absolute maximum occurs at one end point where dy by dx is not 0, whereas the absolute minimum takes place at m1 in between AB where dy by dx is 0. Okay, so absolute maximum, absolute minimum, it is not necessary that dy by dx must be 0. All that you need to do is check the critical points. Okay, first you find dy by dx equated to 0, find the critical points, and then find out the y value. Whichever y value is the maximum, whether dy by dx is 0 or not doesn't matter. Whichever y value is maximum for that value, it is called absolute maximum. Whichever y value is minimum is called the absolute minimum. Whereas, again I'll repeat, for local maxima and local minima, it always occurs at a point where dy by dx is 0. So for local maxima and local minima, the necessary condition is dy by dx must be 0. For absolute maxima and absolute minima, dy by dx need not be 0. Okay, I hope this is absolutely clear to you. Okay, now the second derivative, we are going to do problems based on second derivative test. First I am going to do word problems, then I will come back and do the simpler questions without words, because first I thought word problems are difficult, so I want to finish that first. So what is the method of solving problem? Maybe we'll try it with a question, then I think that will be clear then. I'll just do one problem for you. Now, find two positive numbers x and y such that x plus y is 60 and x y cube is maximum. This is the question. Okay. Now first of all, look for what is given. Now what is given to me? What is given to me is, it is given that x plus y is 60. This is given to me, so I will call this as 1. Okay. So what are the variables? X and y are variables. So what is the meaning of that? For example, I have x and I have y and I have x plus y, and I can also compute x y cube. So if I say x is 1, say y will be 59. When x is 2, it will be 58. When x is 3, it will be 57. In all these cases, the sum is always 60. And for that, correspondingly, you find xy cube and look for what is the maximum value, and that is the answer. But here, to do all this, it's going to be tedious, but calculus makes it very, very simple. As an exercise, you can try this and see. If you have time, you try it and see. The answer will tally with this. We'll see how we go about it. Now what I do, here I want to maximize. What I want to maximize? I want to maximize xy cube. So I will call it by a new variable p. And clearly the quantity, the p, which I want to maximize, will definitely have more than one variable. What are the variables? X and y. I need to change it to a single variable. Now the question is, should I change x or should I change y? It's always better to change x because the power of x is 1, so our calculations will become simpler. So what is x? X is nothing but 60 minus y. I always use the given quantity to convert it to a single variable. You see, that's it. In fact, this is the method for all problems. Identify what is given. Second, identify whether you want to maximize or minimize. It will have more than one variable. Okay, use the given thing to convert it to a single variable. This will be the process for all problems. Of course, the situations will be different. Now, how many variables are there? There's only one variable. And what is the variable? Variable is y. I can differentiate, but I have to use product rule. So to avoid that, what I do, I will open the bracket first. Then I differentiate. What is dp by dy? dp by dy is 180 y square minus 4y cube. Correct? Now I find dp by dy equal to 0. What is this actually? I am finding the critical point. Okay? I am finding the turning point. Okay? So it will be 100. Sorry. I will take y square out. I think I can even take 4 outside. If I take 4 outside, what will I get? 4 4s are 16, 45 I think. Correct? Yeah, I think it's perfect. Now equate it to 0. I'll get y equal to 0 and y equal to 45. Since it's a positive number, I ignore y equal to 0. Okay, that finishes the first derivative. So I differentiated and I found the critical point, nothing else. I just found the critical point. But I want to show whether it is maximum or not. Okay, so for that, what I do, I have to go for second derivative. d square p by dy square. This is called second derivative test. You see, this is what we did here. In the second derivative test, if you see, for a maxima, my second derivative must be negative, right? So I am going to test that. Okay, now d square p by dy square. What is that? It will be 360y. I am differentiating this 360y minus 12y square. Now you can take 12 outside, you can take y outside, you get 30 minus y. Now what do? You substitute the critical point. So it is 12 into 45 and 30 minus 45. There is no need to calculate. You can see clearly 30 minus 45 is negative, so the whole thing is negative. So you have proved that second derivative is negative. Therefore, you can say P is local maxima at y equal to 45. So P is the maximum. Here the maxima and maximum both will be same. Okay. So y equal to 45. So when y equal to 45, what is x? X is equal to 15. It's 45 minus 60. 60 minus 45. Therefore, you can write the conclusion. What is the conclusion? The two positive numbers are 15 and 45 for x plus y equal to 60 and x y cube to be maximum. So I just gave you a sample of one problem. Okay, I think we'll do more problems in the next class. I hope you understood the video. Just it's a difficult topic. Just go through it. If you have any doubt, please put your message in the comment section. I'll get back to you. Kindly subscribe to my channel and click the bell icon to get notifications of video that I post. Thank you for all your support till now. Keep working. See you again in the next class. Have a lovely day.